Okay. Well, this is a spectacular setting to give a talk. I don't think I ever had so much space to walk around ever. When usually you're in a small little but now I can just wander about while I'm speaking, which is always a good thing. So the instructions that Alessandro sent were to give a vision talk, but his explanation was that it should be basically an invitation to work on certain problems. So I was thinking whether to isolate one particular interesting problem or whether to sort of just write some thoughts on slides. And since it's the first vision talk, I did not literally follow those instructions, so I just wrote some thoughts that I had about the subject on some slides with the hope of maybe generating some discussion, because it's always nice to have some discussion at these meetings. Let's see. The clicker, where am I supposed to point in a particular direction, or? Yep, thanks. So clearly one of the most important challenges of theoretical physics is to understand the nature of quantum gravity. And therefore I thought I'd try to write down a few things that I think we have learned so far about quantum gravity from string theory, and a few things that maybe we have not quite learned yet. And by all means, it's also an invitation to disagree with everything that I said. So because I might say something and you might strongly disagree, and by all means, raise your hand and let's talk about it. But one of the main promises of string theory was that it provides us with a theory of quantum gravity. And I think there has been obviously a lot of progress, mostly in the context of ADS-CFT. So there has been a lot of progress in understanding black hole entropy as really corresponding to the counting of a certain set of degrees of freedom, both for BPS black holes and to a lesser extent for non-BPS black holes. So I think it's beyond reasonable doubt that black holes in string theory are just, that the entropy of a black hole in string theory is really counting microscopic degrees of freedom. There has been a lot of progress in understanding the relationship between black hole formation and thermalization, understanding the chaotic nature of black holes, understanding how they scramble information. There has been an amazing amount of work in trying to connect concepts of quantum information theory to quantum gravity results, which always raises the question that I did not write down, is whether we should try to maybe eventually reformulate gravitational theories in purely information theoretic terms, because it's such a powerful language and it has so many important applications. I also think, and this is maybe something that people might disagree with, is that the information paradox has been dealt with satisfactorily by now. I think that's done. However, there are definitely several issues that maybe remain somewhat unsatisfactory. But I would also like to ask the question, where I don't have the answer to any of these questions, but I'd like to ask the question, what is the best we can hope for? Because if a quantum gravitational theory, at least to the extent that we understand it in ADS-CFT, if you're in the quantum gravitational regime, for example, when you create a black hole or you're doing something else, you're in the regime of the dual field theory, where physics is very strongly coupled. It's a large N theory, and it's a very chaotic system. So it's not an exactly solvable system, it's not an integrable system, it's a messy, chaotic system. Now, typically, we do not have any hope to explicitly solve such systems. Like if you want to solve a strongly interacting quantum many-body system and it has 10 to the 26 particles or something, we are not going to solve those equations. So you may ask what actually is the best we can hope for, given the fact that this is a strongly interacting, very chaotic system. And maybe one answer is that the best possible answer is maybe general relativity with a bit more than that, because that's some sort of, if you wish, hydrodynamic description of this very chaotic system. But if someone has a great idea and is convinced that there is much more to be said about these strongly coupled chaotic systems, than what we can do right now, then please let me know. Yeah, so one interesting little, this is maybe the most little technical thing that I'd like to encourage people to think about, is that there has also been a lot of progress in this quantum gravitational context to think about the so-called factorization puzzle and the meaning of wormholes. Wormholes are solutions of the Euclidean field equations with more than one ADS boundary, and alpha vacuum and so on. And I think, again, conceptually, it is by now pretty clear what the right interpretation of wormholes is. They correspond to correlations that arise in the system that arise because a gravitational theory always does a certain amount of coarse graining. If you coarse grain a theory, it becomes a slightly statistical theory, and statistical theories have correlations in them, and these wormholes are just a geometric representation of the correlations that are due to this coarse graining procedure. However, these correlations are not fundamental. They arise as an artifact of the low energy coarse graining procedure. Now, if you take, however, one part of this discussion is incomplete and unsatisfactory, I think. That has to do with the following. So if you coarse grain a high energy sector of a theory, then the spectrum in these high energy sectors of the theory is presumably described by random matrix theory, because that's the universal description of the spectrum of any chaotic, strongly coupled chaotic quantum system. If you want to see the correlations in random matrix theory, so in random matrix theory, different parts of the spectra are correlated to each other, and you can also try to compute those correlations with suitable wormhole-like computations. However, it turns out that the relevant wormholes that you need to write down in order to see those semi-classical, if you wish, correlations in the spectrum are off-shell. So some of the statistics of the theory can be diagnosed with a gravitational theory, but you need to take the theory to be slightly off-shell. And that's a very weird thing, because normally a semi-classical theory is defined as a sum over saddle points. Then in each saddle point we do some loop computations and so on. And we usually don't try to do anything properly off-shell in a low energy effective field theory. But here, if you want to see these correlations, and there's many reasons to believe that these computations are consistent and give us the right answer, we have to do computations that are slightly off-shell. Now, there is a context in physics where we do slightly off-shell computations. For example, if one does so-called constrained instanton computations. But again, I think the theoretical framework that explains exactly when this is allowed and in what sense this is a good approximation to anything is something that we don't fully understand. So I think there's something interesting to be learned from studying the precise rules of the game that explain how to deal with slightly off-shell computations in a semi-classical gravitational theory. Another thing that I think is not quite as well established as it should be has to do with the fate of the infalling observer. If you want, in principle, we would like to do the following computation in ADS-CFT. You give me any state in the CFT, and I am going to predict for you what happens to an observer that moves from the boundary of ADS inward in ADS in that state. That is something that you would like to predict in ADS-CFT. Now, if that state is a high energy state and it describes a black hole or it describes the formation of a black hole, then in particular we would like to explain what happens to an observer, to what is going on in the experience of an observer that falls through the horizon of the black hole, without assuming much. I think many attempts to explain the fate of the infalling observer have a circular argument in them, because you kind of already assume something about the interior, and then you show that maybe that is a self-consistent assumption, but you would like to derive it from the beginning. You would like not to build these things in as some sort of circular argument. And the reason why this is a challenging problem, and I spent several years trying to figure out what the way to do it is, and there's a long, that paper there is the result of 3 years of hard work trying to figure this out, is that it seems very difficult with current technology to unambiguously answer this question. The problem is as follows. So if you have a microscopic state in the field theory that describes a black hole, and you want to unambiguously describe the fate of the infalling observer, from the boundary point of view, what happens is, in boundary and field theory language, is that you basically have a ball of plasma in your boundary theory, which is the dual description of a black hole, and you throw a perturbation at this ball of plasma, and it gets absorbed by the ball of plasma. It's a thermalization process. So from the boundary point of view, what happens is that as this observer approaches the horizon of a black hole, from the boundary point of view, that observer gets thermalized. It becomes part of the thermal bath. And there is a particular time, if you become part of the thermal bath, there is a particular time when you no longer have a simple probe of what went in. So the information of the thing that you threw into this bath gets scrambled all across the bath. And if you then try to probe it with a one-point function or with a simple two-point function, you will not be able to tell that something went into this bath. It will just have thermalized. So from the point of view of simple observables, after a particular moment in time, which normally the time scale we call the scrambling time, after a certain moment of time, from the outside point of view, this observer has just been absorbed by the black hole. And there's nothing there's no trace left. But if you want to reconstruct what goes on once this observer falls through the horizon, you sort of need to still probe later timescales in the problem. And those later timescales in the problem, from the boundary point of view, are very hard to probe, because you threw something in, it got thermalized, and everything got scattered everywhere. Now, pretty much the only theoretical concept that we have that keeps on doing something interesting after the scrambling time is the notion of state complexity. There is a notion of state complexity that basically tells you, given a set of unitaries from an a priori determined list, how easy or difficult it is to go from an initial state to a final state. How many of those unitaries do you need to go from an initial state to a final state? And it's a very detailed quantity because it depends on the details of your set of unitaries and so on. But regardless of those choices, after the scrambling time, for generic choices, you can argue that the complexity of the state still keeps on increasing. And the result of this many-year exercise was that if you really want to unambiguously try to reconstruct what goes on if you fall through the horizon of a black hole, if you want to do it unambiguously, then presumably you need a notion of complexity of some sort or another. And that's a long story. We tried many non-complexity things, they all failed. So the more general question here is, so one question is a zeroth order question. If you have some initial state and you fall through the horizon, what is the probability that nothing happens? Intuitively, because of the equivalence principle, it would probably say that's 1, because why would anything happen? On the other hand, you could imagine, I don't know if you can see my pointer, that your state is such that basically you created some excitation that flows in and that goes in this direction. So from the southwest to the northeast. And if that would mean that once you cross the horizon, you would hit that excitation. And you would like to, presumably that's a very rare event, and the probability that it happens is very low, but you would like to have a mathematical computation that tells you that in a typical state this typically does not happen. And we do not have such a computation right now. More generally, there's still, I think, an interesting question, more generally what the role of quantum computation and computational complexity is in these quantum systems. But the thing that's really holding us back is a precise dictionary between a precise bulk quantity and any precise definition of complexity. This is so far it's a very vague duality where we relate a bulk quantity to something that is morally a complexity quantity, but the precise definition we do not know. And then the last sort of, in this class of questions I would like to ask is, what is the boundary probe of the singularity of the black hole? So we have the question about the infalling observer, but this is also something that I think we haven't really fully answered. You might also wonder whether this is supposed to be a red herring of some sort, but more generally, having a clean criterion in ADS-CFT from the boundary point of view, when the semi-classical description in the bulk breaks down, would be a very nice thing to have. My suspicion is that this has something to do with what you could call a reconstructability problem. Because we're trying to reconstruct semi-classical physics in some region of space-time, and we're trying to make a model of that semi-classical physics in some Hilbert space. In ADS-CFT, it's some sector of the boundary theory. So there should be a map that encodes all that semi-classical physics in a piece of the boundary Hilbert space. Now, as you increase the space-time region, both in time and in space, if you increase the size of the space-time region, and you want to have semi-classical physics being valid everywhere and described everywhere at the same time, then presumably you need a larger and larger Hilbert space to be able to describe all that semi-classical physics. And my suspicion is that there is some interesting relation that tells you that if you have a given region of space-time, that there should be a bound, a lower bound on the dimension of the Hilbert space of states that you need to consistently describe all that semi-classical physics. And I think basically the singularity is nothing more than a sign that by that time, by the time that you reach the singularity, the amount of space-time that you're trying to describe in terms of a fixed Hilbert space is just becoming too large. You're running out of Hilbert space. This is why the semi-classical description must break down. And I wouldn't be surprised if a similar argument could be made in de Sitter, because there are good reasons to believe that de Sitter space, if it makes sense, as a quantum theory, has a finite dimensional Hilbert space associated to it. And if you want to describe de Sitter space for all and eternity, and every single semi-classical process that could take place in de Sitter space in terms of a finite dimensional Hilbert space, then presumably this is impossible. So maybe the fact that you run out of Hilbert space, or you run out of resources, there might be an interesting connection to what in quantum information theory is called resource theory. The fact that you run out of resources might be a way to understand why certain space-times cannot be self-consistently be described semi-classically for all of time. Oh, not too bad. You give me an angry look, right? Yeah. I'll try to stick in the 25 minutes. Then these were some interesting questions within ADS-CFT. Then I also listed a few questions that are maybe beyond ADS-CFT. The first one is that in a much more general sense, if you look at the work based on scattering amplitudes, bootstrap approaches, the swampland and so on, then one output of all of these computations is that you get bounds on the coefficients of the various terms in the low energy effective action. These cannot be anything, there are bounds on the things that you get in the low energy effective action. And especially if you have a gravitational theory, it roughly seems to be true that higher derivative operators really are Planck suppressed. There's clearly some numbers of order unity there, but there doesn't seem to be a nice way to sort of enhance higher derivative operators. So that's an interesting question, because if you could enhance higher derivative operators, if you put a large number in front of them, then the effect of higher derivative operators would phenomenologically become more important. So from a phenomenological point of view, the fact that we, if you could put these bounds really rigorously on it, I think it's only done with certain assumptions and in certain context, if you could really put rigorous bounds on this, you would also put strong limits on the extent to which we ever are able to hope to see anything quantum gravitational in the cosmos. And maybe the conclusion of all of this is that it's super unlikely, because all those higher derivative terms perhaps are just very small and never really relevant. And it would be very important to nail this. Because if it's true that higher derivative terms are really not that important ever, that would be an important lesson. It would also be a slightly depressing lesson, because that would make it even harder to see any interesting quantum gravitational signature in the universe. An entirely different way to try to understand quantum gravitational theories is not to do the ADS-CFT game, but to look at different decoupling limits that you can take. And a famous decoupling limit that you can take in M-theory is something where you put M-theory on a circle, a space-like circle, then you take a limit where you make the circle null. You keep the number of momenta that go through that circle fixed. That's a conserved quantum number after all. That's the number n. And then you boost the circle into a null circle. And you can argue that in that limit, it's a very strange limit. It's called discrete light cone quantization, because we have a compact null direction. So you have to be very careful what you mean by that limit. And in some sense, it's also, again, a weird, strongly coupled limit of M-theory. But in that limit, we get a very simple quantum mechanical system. It's called BFSS theory. You may have heard this is an old thing that was invented in 1995, basically. So it has been around for almost 30 years. And it's, in principle, a very simple theory, because you just take n equals 4 super Yang-Mills theory in 4 dimensions, and you dimensionally reduce it down to 1 dimension. And then you have some quantum mechanical theory, and that's BFSS. So in principle, it's a relatively simple theory. It has some fermions, a gauge field, some scalars, but it's notoriously difficult to compute anything. But if you want, there is a super simple dual on paper. You can write down the equation of M-theory in flat space. So it's not ADS, it's flat space. And it would be wonderful to attempt to try to get a bit more out of BFSS. So one interesting thing you can do is you can put BFSS on a computer and you can numerically simulate it at finite temperature, and you can see whether the thermodynamics agrees with the thermodynamics of a black hole in M-theory, and it works. So you can actually do some numerics. But as far as important fundamental questions in quantum gravity go, I think we have so far not been able to employ BFSS very much. And BFSS is part of a much larger class of decoupled theories that all describe different corners of string theory. For example, if you throw in an extra circle in M-theory and you do again this discrete light cone quantization, then we get a 1 + 1 dimensional theory. It's called matrix string theory, which again looks deceivingly simple, but unfortunately we have not been able to very successfully use to do something proper quantum gravitational. What you can see is that you get the spectrum to come out okay, and you can maybe see that type 2 supergravity lives correctly in it, but we have not been able to get much more out of it beyond that. Another observation I wanted to share is that, well, quantum gravity is a non-local theory. And the reason why the information paradox has been resolved is basically, a breakdown of locality. One formulation of the information paradox is what was the mistake that Hawking made in his computation of Hawking radiation, where he did a semi-classical computation. Well, the mistake, between quotation marks, it's not really a mistake, but the thing that breaks down in the full quantum theory is locality. Because if you do a semi-classical computation of Hawking radiation, but you allow for very tiny non-local effects at all length scales, they should not be confined to a finite size, they have to be on all length scales. But once you allow for non-localities on all length scales, information can come out. And that's the main lesson from all the studies in ADS-CFT. So locality breaks down, and that in particular means that if you have a gravitational theory semi-classically, you cannot take two regions of space-time and factorize the Hilbert space, because it's a non-local theory. You cannot really do that. You can do it in the semi-classical theory approximately, but in the full quantum theory, this does not really make sense. It's still, however, interesting that if you think about ADS-CFT, and you think about the RT surface that computes entanglement entropy, is that somehow there is a very distinguished role for extremal surfaces in ADS-CFT. Because in extremal surfaces are the boundary of what's known as an entanglement wedge, and those are the regions in space-time, so that is this very tiny little green region here. Those are the regions in space-time that can be efficiently reconstructed from a part of the boundary theory, where you do have an approximate factorized piece in the Hilbert space, because it's associated to a spatial region in the boundary. So somehow, locality works almost as well, locality works as well as it possibly can across extremal surfaces, but not across general surfaces. So apparently there's something important about thinking about the location of extremal surfaces in any gravitational background, because somehow it tells you something interesting about the way the underlying degrees of freedom are organized and entangled with each other. But we don't really understand the rules of the game here very well either. But it's something to, I think, worth thinking about. Another cute, so I just listed some observations. I have one more slide and I'm done, and then you can disagree with me. But, another little observation, I think it's amusing, is that so black holes are believed to be described by typical states or superpositions of typical states. And all typical states, well, almost all typical states are supposed to look like a black hole in practice. But there seems to exist a basis for the black hole Hilbert space of atypical states that at one moment in time look very different from a black hole. If you would then take those states, those will not be energy eigenstates, because if you take those states and you let them run for a little bit of time, they will still collapse and make a black hole, so they're not energy eigenstates. But there is some evidence that there exists such a basis of states. That means that in some sense, at least at one instance of time, you can sort of disentangle the black hole, if you wish, into its individual constituents. That's a remarkable thing. I'm not sure how rigorous we believe that, but there are very good also theoretical reasons to believe that this is possible. And I wonder if this is useful for something or just a weird observation. You might hope that you can learn something about the black hole, but you cannot use it to do any scattering, because the time scale for scattering is much longer than the time scale for collapse of these states. So maybe it's more like a theoretical fun observation rather than something very practical. But you might hope that at least at one moment in time you can sort of disentangle a little bit what the interior structure of the black hole is. You may also have noticed that in the last few years there was a lot of excitement applying methods of algebraic quantum field theory to questions in quantum gravity. I think so far most of those methods are very much limited to semi-classical gravitational computations. At a technical level, what one can do with these von Neumann algebras is try to explain some entropies of black holes and other things that you see in certain spacetimes. Not just ADS, but also in flat space and in de Sitter. By playing games with algebraic quantum field theory in these backgrounds, you can understand some, you can more or less understand some of the entropies that you compute in these backgrounds. But this von Neumann technology so far is not a full quantum gravitational approach to the problem. Because in ADS-CFT, for example, if you take a black hole in ADS-CFT and you apply this von Neumann machinery, you get what's known as a type 3 von Neumann algebra. That's a fairly generic type that you find in quantum field theory. Then it's very interesting that if you add an observer to these backgrounds and you combine the starting algebra with a little algebra of the observer, so you add some external degrees of freedom to the system, which in principle is not supposed to be allowed because the observer is part of the system. The observer is not supposed to have some independent God-given Hilbert space. But if you nevertheless take a background and you add an observer and you give that observer some its own little piece of Hilbert space, and you look then at what happens to the algebra, then it changes from a so-called type 3 to a so-called type 2 algebra. And in type 2 algebras, you can define things like traces, which in type 3 algebras you cannot. This is why once you add an observer, and you can define a trace, then suddenly you can define things like entropy, up to some normalization constants and so on, and some other technical details. So that's nice, but the thing I think that's kind of missing in order to make this into a real tool for actual quantum gravitational questions is to go from a type 2 to a type 1 algebra. Because a type 1 algebra, that is literally the algebra of operators that you have in a CFT on a cylinder. Or on the plane. That's a type 1 algebra. Those are the simplest possible von Neumann algebras. And if we are not going to understand how to go from a type 2 to a type 1 algebra, then this von Neumann algebra approach will have limitations as far as getting actual quantum gravitational lessons from it. It has, for example, although you can compute entropies by taking traces, it has not elucidated really the underlying microscopic degrees of freedom, because those traces, they're not literally the traces over a Hilbert space, there's some other trace. I think it's also interesting that there seems to be some advantage of adding external observers to systems. It somehow makes the problem more well defined. And it's easy to understand why, if you, for example, have a closed universe, it's great to have external observers added to it, and why it gives you a lot of technical power. That's simply because in a closed universe we don't have observables. It's very hard to define a good observable, because there's nothing to hold on to. Every point is related to every other point by some diffeomorphism and so on, so you have nothing to hold on to. In ADS-CFT we have the boundary to hold on to. All observables we define in ADS-CFT are with reference to the boundary. But in other spaces, we don't have these boundaries, and we have nothing to hold on to. But once you add an observer to one of these spacetimes, suddenly there's something to hold on to. You can define an observable with respect to the observer. And that's why suddenly the whole technical machinery becomes much more powerful. But the price that you pay is that you add an external Hilbert space to the system. And on the one hand, it's good, because you all think you're conscious beings, and you all think that you have maybe a Hilbert space in your brain that you can independently manipulate. And maybe that's the kind of Hilbert space that we're talking about here. So it's maybe a good model of consciousness and intelligence and reality and so on. But ultimately, in a closed universe, everything should fit in one big system, you think. Unless, well, in this setting, unless, of course, there is something super, you know, that our mind is not really part of this universe and it's part of a bigger entity, and like over there or so. Another thing that I think is also interesting is ADS-CFT is very powerful because it's a boundary value problem. We have a boundary, it's a conformal boundary, but we have a boundary, and we define a boundary value problem. And you can ask, well, can I not put boundaries anywhere and define other types of interesting gravitational boundary value problems? Because I can put boundaries in other spacetimes, I can put boundaries in flat space, I can put boundaries in de Sitter. Can we not use that to learn something? Yeah, presumably you can learn something, and a lot of work recently has been done. For example, TT bar deformations are believed up to issues that they correspond to moving boundaries inward. A lot of the work on brain worlds and so-called double holography uses brains, end-of-the-world brains, and basically boundaries of space-time. And maybe there's maybe, well, I wouldn't be surprised if we can learn much more from this approach as well. The general drawback is that if you put a finite boundary in space-time, is that the theories on the boundary tend to be non-local. You can already see that in the TT bar example. And that means you have to start to think about non-local dual descriptions of species of space-time. And then clearly, you know, it's all much less powerful because it's all non-local and everything. But clearly it's worth exploring a bit more. And then the last two things I wanted to briefly say is, the first one is that there has been a lot of work recently on something called celestial holography. The work so far is almost void of holography. It's looking at scattering amplitudes in flat space and reinterpreting those amplitudes. It would be nice to put a bit more holography in celestial holography. And the first thing that you might want to do is try to stick a black hole in flat space and see what that means in this language. That's very different from ADS-CFT because a black hole in flat space is unstable. It will evaporate. But maybe a great warm-up exercise is to first go back to ADS-CFT, because if you're well below the ADS curvature radius, you effectively have a piece of flat space as well. And if you put a black hole in that flat space, those are very tiny black holes from the ADS-CFT point of view. I don't think we know the dual description of those black holes in ADS-CFT either. So it might be a nice warm-up exercise in order to try to see what black holes in celestial holography mean, is to rethink what tiny black holes in ADS-CFT actually mean. And the final thought that bothers me is that it is extremely difficult to find weakly coupled de Sitter vacua in string theory. Maybe they don't even exist. So then perhaps we should just stop working on de Sitter, because it's a wrong question to ask. If it's true that there are no weakly coupled de Sitter vacua in string theory, but all cosmological solutions have rolling scalars or other features, then maybe we should try to do holography for all those other solutions and not for empty de Sitter. Maybe it's a misleading question to ask about the holographic dual description of de Sitter. Maybe it's just a misleading question. And the fact that it's so hard to find weakly coupled de Sitter vacua, it feels like the world is trying to tell us something. Because on the one hand, you can make arguments that there should be like billions, and then on the other hand, you can't find a single one. So there's something really strange about the whole situation. So somehow I think there's something here that we're missing. And that would be, I'm not sure what. If I knew, then I would work on it. But I feel like we're missing something important here that we need to think about. So I'm not even sure we're asking the right questions in this context. Certainly we can do scattering amplitudes in de Sitter, you can do quantum field theory in de Sitter, that's all fine, but if you want to do a proper quantum gravitational version of de Sitter, I honestly don't know whether we're asking the right questions, and I'll leave you with that. Thank you.
Thank you, Jan, for posing all these very interesting and challenging questions. Maybe somebody already has answers or comments or more questions. Yes? Or objections?
So thank you for your very nice talk. I'd like to ask about the possibility you mentioned that it is possible to predict the future of the history of an infalling observer into a black hole from the state in the boundary. But wouldn't that mean that it's possible to obtain information from the black hole interior at the boundary asymptotically? Isn't it strange?
Yes, well, in principle, if you have only one boundary, we do ADS-CFT with one boundary, and we choose a state in the boundary theory that, say, describes a shell of matter that collapses into a black hole, but it's all in one side. And that state and that single theory should know everything about the gravitational interior, in principle, according to ADS-CFT. So in particular, it should also know about the inside of the black hole. That's part of all the information that is possibly available is in that one state, including the interior of the black hole, if it exists. It should all be there. Is that your question, or?
More questions for Jan? Maybe a quick one from myself. About the idea that you can maybe use minimal surfaces to sort of split up the Hilbert space. So in many interesting cases, there are more saddles, so you can actually need to sum over minimal surfaces. Just taking one would not suffice. So what do you think that could tell you already about the impossibility of separating Hilbert spaces?
Yeah, that's good, thanks. Yeah. Yeah, if you ask a question about, say, entanglement entropy or things like that, and we are instructed in principle, then there could be more than one extremal surface. Then normally you take the one that minimizes. It's usually the answer to some minimization problem. But there can be more. But there is interesting information also in these other extremal surfaces. All extremal surfaces, regardless of whether they are computing the entropy for you, they are on some sort of information barrier of some sort. So in that sense, finding them all is still an interesting way, and maybe one can reorganize the physics somehow in this surface language, because there's somehow information barriers. So it's a bit in this direction of trying to reformulate things more in information theoretic terms. So for example, some of these quantum extremal surfaces, they're related to like these Python lunch type phenomena, where you have pieces of space-time that are exponentially hard to reconstruct from the boundary point of view. That again, so those again act as some sort of information barrier, because it's very hard to connect the information from the outside to the information on the inside. So that's why also all these subleading ones in principle are interesting, I think.
Thank you. So there will be much more time for questions during the breaks if people want to approach Jan and discuss. For the moment, let's give him again a big hand.